Hello, and welcome to another wonderful day of chemistry when we get to learn about some amazing new things. Today, we're going to learn about some really cool stuff. It's a lesson on light and what light and atoms have to do with each other. And I got to tell you, light is one of my favorite things to talk about. It's one of my favorite things to explore and do a little experiments with. So I hope you enjoy light as much as I do, and may this enlighten you today. Today we're going to be talking about the arrangement of electrons in atoms, and our objectives are to look at spectra experiments, okay, by a gentleman by the name of Bohr, and look at his model of the atom, and then you should be able to describe that, and then explain how light emitted by atom gives off information about electron energy levels. So when you come out of here, you should be able to explain how the atomic spectra, we'll talk about what that is, are created and why they contain only certain wavelengths of light. And then we're going to talk about what you should be able to get out of here and be able to explain the connection between the atomic spectrum of hydrogen and the energy levels of the Bohr model. So let's talk about our story. Our story starts in the pre-1900s, right? Okay, where did we start? We have models of Dalton, little billiard ball. Thomson, plum pudding model, right? Rutherford, the typical central nucleus with the electrons zipping around the outside of it. But we started looking at light, and we started looking at atoms. Different scientists were studying this stuff, and they started coming up with a thought that said, you know what, we don't think that Rutherford's model is correct. There's more to it. And so let's talk about light a little bit. What do we understand about light? Before 1900, we understood that light was a wave, and so it was characterized by certain things like wavelength. This is a little symbol. It's called lambda. It kind of looks like an upside down Y. And lambda is the wavelength, and we measure it in distance of meters, nanometers, things like that. And then light was also characterized by frequency. The vibration, the number of times it would cycle per second, which we talk about in terms of hertz. Hz stands for hertz, okay? And then when we looked at that relationship between frequency and wavelength, we realized it was an inverse relationship. And that relationship there described the speed of light. C is the speed of light. So the speed of light is equal to the wavelength of light times its frequency. And so basically, if you change the frequency and the frequency goes up, then the wavelength must be going down. If you increase the wavelength, then the frequency must be going down. These things have a relationship that is inverse. And so the speed of light, which it was first roughly calculated in the 1600s, by looking at the amount of time it took light to go from Jupiter to the Earth in different times of the year during an eclipse. Pretty cool, right? The speed of light is calculated today at about 3.00 times 10 to the 8th meters per second. And remember that all electromagnetic radiation, microwaves, radio waves, light waves, gamma rays, all of this stuff is traveling at the same speed, okay? They're all forms of light, in a sense. We call them electromagnetic radiation, but they all travel at the same speed. So here's a small little clip of what we see. We see stuff in the visual spectrum here, right? Red, orange, yellow, green, blue, violet, indigo violet. We can see light that is in this little spectrum, but look at how huge this spectrum is. From really long radio waves to microwaves, okay, this is where you can see TV and hear radio. Infrared, which they're using to measure your temperature now. Ultraviolet, which gives you sunburns. X-rays looks at your bones. Gamma rays, which are dangerous, and no, they don't turn you into the Incredible Hulk. They would kill you before that. All of these are the huge spectrum. These are the smallest little wave lengths and the fastest frequencies. These are the biggest wavelengths and the smallest frequencies, okay? So that's the electromagnetic spectrum. But as we were going into the early 1900s, people including Einstein were starting to say, you know what, light might not be just a wave. What else could it be? Well, first of all, Max Planck started doing some experiments, and he thought about these hot objects, and if they're emitting energy, are they emitting energy continuously? No, they're not. They're only emitting energy at certain times, at certain heats and certain energy amounts. And so then we had to say, okay, well, if light is a wave, then any light should be able to remove electrons from metal. And they found that that wasn't true as well. Einstein did some experiments with the photoelectric effect, as well as Planck. Einstein then proposed, you know what, maybe there's only certain frequencies of light that can actually remove electrons. So light and electrons have something to do with each other. Light, when it hits an atom, can knock off electrons, but not all light knocks off all electrons, right? And so what they did, again, this is that photoelectric experiment, okay? It's called photoelectric effect. And they shot the light at a piece of metal, and sure enough, at certain frequencies, electrons would come off, and they would jump from this piece of metal onto this area here that was able to basically connect the battery. So they'd see that there was an energy discharge coming at certain frequencies of light. But it didn't work for everything, right? And so what this told Einstein is that light was behaving like a particle, not a wave in this case. Let's look at a couple more examples. They started theorizing that energy was coming in the form of photons, okay? These waves that were kind of packaged inside little particles. And like I have 3 photons coming here, I have 3 ejected electrons. That was kind of interesting. If you look here, we see that it took certain energy levels. Red light, which didn't have enough energy, emitted no electrons. Green light, which had 2.2 electron volts, was emitting electrons at a particular velocity. But the violet light, which was at a much higher electron volt, okay, a shorter frequency, shorter wavelength, higher frequency, was giving a greater amount of velocity to the particles that are coming out of it, to the electrons that are coming out. And so this was telling them that the electrons were somehow associated with the amount of energy that was coming in the form of light. Okay, well, that says something interesting, right? Objects can only absorb or emit energy in certain quantities. So Max Planck basically said, you know what, we're going to call these quantum of energies or quantized energy. So I want you to start thinking of light in terms of packages. Those photons have certain packages of energy, okay? And so a certain package of energy might be able to knock an electron off, but a package of energy that doesn't have enough energy, okay, so here's another package that doesn't have as much energy, can't knock the photon off. So it takes a certain quanta of energy in order to be able to knock electrons off. Think of it this way. You know, they thought before that maybe there was a continuous spectrum, but they were starting to realize, no, it's not like a continuous spectrum, like a ramp that you would move up as you're going along energy levels. It's actually like stairs, where you can't exist in between. You only exist at certain levels. And these electrons only exist at certain quanta of energy. These electrons, they were figuring out, they can behave like waves as well, really, and they will jump from one energy level to the next, but they won't actually exist in between. They basically jump from one step to the next, just like you would go from one step to the next as you're going up the stairs. So why can't they be both? Why can't light be both a wave and a particle? Can you see it? Wave, W-A-V-E, and particle, P-A-R-T-I-C-L-E. Kind of fun, right? Light was behaving as both. So when you're shining a flashlight, you've got all of these little photons coming out. They have all these different little frequencies of waves. And, you know, if you're looking through white light, or looking at white light, okay? So here's a flashlight, right? And if I can take and I can break that light up, it's going to end up with some pretty cool different effects. I hope you can see that and see that there's something kind of cool happening there. Maybe you can't. I don't know. Boom versus boom. I don't know. Anyway, that paper is a spectrum paper, and it's able to break the light up into various different frequencies. And so all these different frequencies of light that are in white light can get broken up. It's kind of cool. So again, light has a dual nature, behaves both like a particle and like a wave, and can do it in different situations. And so we have a new name for what we talk about with a particle of light, and it's called a photon. And again, it's particle and wave-like in nature. It has zero mass, but it does have a particular quantum of energy. Okay? So going back to our original question, what does light have to do with atoms? Let's talk about it a little bit more in detail. When we energize particular atoms, what's going to happen? So what they did is they took and they had basically just general white light source. They emitted white light, and they got the full spectrum. But then they decided, let's not just take this general thing, let's take specific elements. So they took some hydrogen gas, and this is only filled, this little tube is only filled with hydrogen gas, and then they electrified that. And what happened when that light came out, and it still looked white, but it wasn't just white. In fact, it had just specific wavelengths of light in it. You can see there's different little colors here, different colors here. Hydrogen was giving very specific lines of light or quanta of light. It was giving very specific wavelengths or quanta of light, not the full spectrum, just pieces. Oh, okay, so Niels Bohr is looking at that and he's starting to think, what's happening here? Something is interesting, and I wonder if we can explain it in terms of what the atom looks like. Okay, so if we looked at the classical light theory, we would expect atoms to be excited by whatever energy they absorb. Here comes some energy. I'm excited. Let's go ahead and give off some, electrons. But that wasn't happening. It was only certain wavelengths of light, right? So since it's only certain wavelengths of light that emit the electrons or that get the atoms excited in terms of electrons jumping up different energy levels, we call that the line emission spectrum. Okay, so this is the line emission spectrum, that it gives off just certain colors. What's happening there? Well, Bohr thought, you know what? Oh, this is a little hard to see here. But basically, what we have here is we have the nucleus here, and then we have these electron levels, okay? And so they're showing 3 different electron levels here. They've got 1 electron here, 1 electron here, 1 electron here, okay? So if the electrons are circling the nucleus, this is Bohr's idea. He kind of thought it was like a planet. So we call this Bohr's planetary model. He kind of thought it was like a planet around the sun. So he's like, okay, if they're circling the nucleus in defined paths or orbits, and they can't be in between the orbits, okay, they either have to be here or be here, they can't be in between, then maybe this will explain what's happening. Maybe it takes a certain quantum of energy to be able to make them jump from one level to the next. Okay, and so he realized that the further out they are from the nucleus, the more energy would be required, okay, to keep them there. Or if I want them to jump further away, it would take even more energy to jump them further than closer, right? So he came up with this atomic model, excuse me, that put the electrons in various different energy levels. All right, so how do we create these atomic spectra? Well, here is a little spectrometer, okay? And this is something that you can look through. And if I look at the light, it's really cool. It turns into a rainbow inside. And if I look at very particular light, like light that comes from hydrogen or light that comes from neon or something like that, if I look at light that comes from these fluorescent bulbs, I actually see the different energy levels in a sense because I see the different colors that come off. And it's not a full rainbow. When I look at the fluorescent bulb, there are very specific colors that are shining from it. And it's not the full rainbow that you see. You see very particular lines. It's really cool. Okay, very specific lines that show up instead of the full rainbow. And that is what is being created by the the gases that are exciting the phosphor that's inside of the fluorescent tube there. All right, so how do we create these spectra? Well, electrons are going to jump from their ground state to an excited state. They jump from a lower energy level to a higher energy level. That's what happens when they get excited, okay? So here comes a photon. The photon hits this electron that's around the nucleus. This electron is in its ground state. And as soon as that photon strikes the electron, it gets excited. And it jumps from one energy level to the next energy level. It goes up an energy level. That's its excited state. But it can't stay there for long, okay? And it's really, again, this is Bohr's model. And so he was thinking of them jumping. But today, we kind of realize, yeah, there is a different distance from the atom that happens, but it's also about their vibration. So I really want you to kind of be thinking about vibration. Like here's the vibration of this electron, and when it gets excited, it vibrates faster. Okay, so it jumps and it's vibrating faster, but it can't hold that for very long. It's in an unstable excited state. It falls back down. When it falls back down, here's the picture. When it falls back down, then it gives off a photon of light. So the electron gets excited when light hits it, jumps up higher, and then when it falls back down, then light shoots off. And that's what's happening. And that's how we get these different spectra of light. Every element has a unique line spectrum, and what's happening is it's the different spectrum that they have is all about the different electrons and the different energy levels that they're dropping. Okay, so here's hydrogen's spectrum. Again, that's the line spectrum. You see 4 lines there. Well, let's look at what is happening? You know, if I have an electron that goes from this first energy level down here, it gives off this color of light. If I go from the second to the first, it gives off green. If I go from the third to the first, it gives off blue. So the further it jumps back down, the higher the energy frequency is of the light that it gives off. Blue light has a higher frequency than green. Green is a higher frequency than red. These different colors that we get are from the different energy levels of the different electrons jumping different distances, okay? So that's how you get that, right? So when the light's being given off, it goes through the prism and it makes these lines. Now, his model was great for hydrogen and it explained it. But mathematically, when he tried to apply the same formulas, and again, there's some complicated math behind all this. When he tried to apply the same formulas to other elements, it didn't work. So there was something even more complex going on. And we'll learn more about the different model that comes after this. But the formulas didn't work out for everything except for hydrogen. And it worked for hydrogen, but things got more complex. So, great that it worked out, but the math was a lot more complex, and then the model had to become a lot more complex. We'll learn more about it later. But let's look at a couple different spectrum. We've got hydrogen. Here's heliums. Again, notice that each of these is unique to the element. We call these the fingerprints. Okay, these emission spectrums are like the fingerprints of the elements because they're unique. And these fingerprints were ones that allowed us to see elements on this planet that we didn't even know existed. In fact, we discovered helium on the sun before we discovered it here on Earth. Because we used one of these little guys, a much more complicated one, looked up at the sun and saw this emission spectrum that we'd never seen before here on Earth. We're like, what is that? And they're like, well, it must be a new element. And in fact, it was a new element. And they're like, well, I wonder if it's here on Earth. And they started looking for it. And guess what? They found it. Okay. Helium was discovered on the sun before it was discovered here. Pretty cool. And then, of course, they started looking into helium gas and saying, wonder if there's other things that doesn't react. That's the reason they didn't know it existed, because it didn't react with anything. And it was this inert gas. They're like, I wonder if there's other inert gases here. And in fact, they did some more research, took this helium gas and divided it out by temperature. And they started finding neon and argon and krypton and xenon and radon. They found all these other gases that they didn't know existed. All right, so Bohr model of the atom, planetary model, right? If we were to draw the nucleus with the protons and neutrons, and then 3 energy levels, 1, 2, 3. Then we could show the electrons, that are surrounding and moving around the atom. And he thought it was like a planet, okay? And it's a way more complicated than that. But it's still a good model. We still use this model today to help understand how the atom actually is represented. It just kind of it's easy, and so we like to use it. So we use it still even to this day, even though it's not exactly accurate. All right, so well, these are the next objectives. Sorry, I'm going to the wrong spot there. So can we now look at and describe Bohr's model of the atom? Yeah, we now know it's a planetary model. We understand emission spectrum, that the emission spectrum are the different colors of light that are being given off by different frequencies of wavelengths of light, right? So electrons jump different levels. They give off different colors of light, different frequencies of light. We know that electrons and light are quantized, that they have certain vibrations and certain energy that they can give off as they jump back down and as they're given off or jumping up. So for instance, if red light were to hit an electron, it would jump a certain level, and then when it falls back down, it's going to give off the red light. So it's a particular energy that gets it excited to a particular level, and it's a particular energy that it'll give off when it comes back. Yeah, anyway, I think we've covered those objectives. I should have put them back up there on review, but you can go back in the video and double check to see if you know what you know, but I bet you know the objectives just fine right now. Anyway, light's awesome. We'll learn more and talk more about light later on. But I encourage you to explore light, explore the quantum theory as we get into that. there's some pretty crazy stuff about light that just blows your mind. And you'll learn about it more in physics too. But it is one of the coolest things to study. So look into it. There's a cool book called QED, which I read if you're geeking out about light. And it's a pretty awesome exploration of what's actually happening with light, and it's just going to blow your mind if you get into that quantum theory stuff. It's quantum electrodynamics is what QED stands for. Anyway, cool stuff, and I hope you had an awesome time learning about it. I had a great time teaching you. God bless. Be kind to each other.